let me give a short introduction to Professor Richard J. Roberts, who won the Nobel Prize in Physiology and Medicine in 1993. Since Professor Roberts has a good bit of biography built into his presentation already, I'll cut my introduction relatively short and hand things immediately over to Professor Roberts. So a big round of applause for Professor Roberts, please.
Okay, well, thank you. What I'm going to try to do today is to talk about my own life in science, how I got interested in science, what subjects I studied. I'm going to talk about two things that are quite important or have been very important for me. One of those is luck, and the other is the importance of failure. These are two things you don't hear much about usually in a scientific presentation. And I will tell you how these led me to the Nobel Prize, and then I'll talk a little bit about some of the stuff that I've done since I won the prize. Now, I grew up in the United Kingdom, and on the left-hand side, you will see a site marked A, that's Derby, that's where I was born. I moved from Derby to Bath and grew up in Bath. I went to junior school, St. Stephen's School in Bath, and there I fell in love with mathematics and really discovered mathematics in a big way. And I also read a book about how to become a detective. And by the time I finished that, I realized that I was going to be a detective. By age 11, this is Bath, which is a very beautiful city. If any of you have not been, you should go and visit. But while there, I discovered chemistry. My father bought me a chemistry set for Christmas. And there I learned to love fireworks and explosives, because in those days, the chemistry sets were fun. They were not full of rubbish that didn't really allow you to do any interesting chemistry. For grammar school, I went to the City of Bath Boys' School. I increased my love of mathematics, learned to play the violin and so on, and went and really had quite a good time there, although I didn't enjoy the physics master there. When I was 17, we were learning to take the material that was necessary to take the advanced level exams. And I stopped going because it was very boring. They were just repeating everything that I already knew. I got caught. I used to go and play snooker and billiards during the day and then go and sign off at night. And I learned one of the most important lessons of my life playing snooker. And that was that when you have a lucky shot, one that you weren't expecting, you have to make the most of it. And I learned this from an old gentleman who came and told me after I'd had a lucky break and didn't take advantage of it. And that's something that stayed with me my entire life. And I think it's very important to see where luck has sent you one way rather than the other, and then to ask, did you really take advantage of that luck? When it came time to go to university, I went to Sheffield University. I'd actually failed physics at the A levels in my first attempt and had to go back and redo it. So that meant that Cambridge and Oxford were off the table for me. In Sheffield, I did chemistry. I really then went and worked in Professor Ollis's lab. He was head of the organic chemistry department at the time. And I started my PhD with him. But the really important person is shown on the next slide, and that is Kazu Kurosawa. He was a postdoc in the lab, and he was my real mentor in Sheffield. And so he taught me how to do chemistry. And as a result of that, by the end of the first year, I had all the results I needed for my PhD. But of course, in England, you have to spend 3 years doing your PhD. One of the other things that Kazu taught me was how to play Go, this game shown on the left, which is a very interesting and complicated game. It's more complicated than chess, and really a very, very good game. But during the third year of my PhD, I spent a lot of time in the library and read this book, The Thread of Life by John Kendrew. Kendrew was a Nobel Prize winner, and he really discovered how to determine the structure of proteins. But this book was all about the origins of molecular biology. And by the time I finished the book, I figured this was what I was going to do with my life. I was going to become a molecular biologist. And so I applied to a number of labs to do a postdoc, and the person who picked me up was Jack Strominger. That's this man. And when I applied to him, he was a professor in Wisconsin. And so I thought I was going to go to Wisconsin in order to do my postdoc. But about 2 months before I was scheduled to go, he called and said, "Can you delay for a month? Because I'm just moving to Harvard. I've just been made a full professor at Harvard," which turned out to be his lifelong ambition. So I ended up again, by chance, luck, going to Harvard instead of Wisconsin. And that turned out to be very, very good. While I was a postdoc with Jack, I learned how to sequence tRNA. And one of the things that I did when I started, I was following a rather old method because I picked the project up from a postdoc an Australian postdoc who was using the original methods for sequencing RNA. But when I started reading about this, I discovered there was a better method. Next slide, please. And this was a method that had been discovered by Fred Sanger, shown underneath the red arrow here. And he already was a Nobel Prize winner at the time. He'd won the Nobel Prize for determining protein sequences. And in 1969, I went to Fred's lab in order to learn how to sequence RNA using the new methods that he'd been developing. I spent 6 weeks in the lab. I made copious notes, came back to Harvard, and Jack Strominger had lots of money and put a sequencing lab in where I was working. And I, as a result, ended up being the first person in the Boston area to be using Fred's methods for sequencing RNA. And a lot of people came to me to learn how to do it. And that turned out to be really very good. I met a lot of very nice people, important people then. And at the time, I was thinking I was going to go back to England and, return to England to try and get a job. And I'd met someone from Edinburgh who said there was a perfect job in Edinburgh for me. And so I sent in a letter, but that letter I never got a reply to. In the meantime, I got 2 offers to work in the US. One of the offers was from Jim Watson, who was the head of Cold Spring Harbor Lab at the time. This is Jim Watson of double helix fame. And I was also offered a job at Harvard, but actually Cold Spring Harbor seemed more interesting. And so I went into Jim's office, and he'd never met me before. And I talked to him maybe 10 minutes, maybe less than that. And he offered me a position at Cold Spring Harbor. And what he wanted me to do was to sequence the DNA of a small tumor virus called SV40. And that sounded okay. The way that one sequenced DNA in those days was first to copy it into RNA and then to sequence the RNA and determine what the DNA sequence must have been. So I accepted the job, but before I went and listened to some lectures. And again, this points out the importance of listening to things outside of your immediate subject area. I went to this lecture over at Harvard Medical School given by Dan Nathans, who is the figure in the top left here. He was talking about a new enzyme called endonuclease R, which is a restriction enzyme that recognizes specific sequences in DNA and cuts whenever it finds those sequences. And it turned out he'd been using this to map SV40 DNA and to find out where the genes were in SV40. And it occurred to me that one might be able to use this enzyme and others, if they existed, to sequence DNA, to do it directly instead of copying it into RNA, but to isolate small fragments of DNA and then to sequence them. And so I thought, when I first went to Cold Spring Harbor, that instead of copying the SV40 into RNA, and I learned that there were 2 other labs already doing that one of the things that I would do would be to look and see if I could find some more restriction enzymes and use those in order to develop a method for sequencing DNA. Well, when I got there, I discovered that there were actually 3 more enzymes that had already been discovered. So I immediately made those and then started looking for more. And so during the 1970s, I actually moved to Cold Spring Harbor in 1972. And during the 70s and early 80s, 75 of the 100 known type 2 restriction enzymes were isolated in my lab at Cold Spring Harbor. And these turned out to be important, not for sequencing, but rather for recombinant DNA, to use A, to make recombinant DNAs, and B, to characterize them once they'd been made. I might add that Dan Nathans, Werner Aber, shown in the middle, and Hamilton Smith at the bottom, won the Nobel Prize in medicine in 1978, and this was for the discovery of restriction enzymes. They had made all of the key advances in the field. Now, one of the things that happened when I got to Cold Spring Harbor, Jim Watson got very annoyed because I wasn't sequencing SV40 DNA using RNA methods, but instead I'd been diverted and started using restriction enzymes and making them, and everybody was interested in those, and they turned out to be more interesting than trying to sequence SV40. And Jim was not happy with that, and he often tried to fire me from Cold Spring Harbor. But I was lucky. I met this gentleman, Norton Zinder, who was a professor at Rockefeller University, and he was a very good friend of Jim. And he also loved restriction enzymes. And so he thought that what I was doing was absolutely right, more important than trying to sequence SV40 using RNA. And so he would often rescue me when Jim suggested he was going to fire me. And I think this is also a good lesson that I learned. It's good to have friends who can help you and can make sure that you continue doing the right thing, even when some other people tell you you're doing the wrong thing. Now, while I was at Cold Spring Harbor and making these restriction enzymes, we started to use them in order to map adenovirus 2 DNA. But we were also interested in transcription, in how adenovirus DNA was making RNA. And early in infection, on the right-hand side, you can see by the arrows that there are 4-5 main transcripts that are being made. And we wanted to know whether the sequence that in the DNA that said start making these transcripts, it's called a promoter, whether this promoter was the same in adenovirus, in a eukaryotic virus, as it was in a bacterial virus. And we were interested in this because the sequence of a promoter in lambda, bacteriophage, and also the lac operon had been determined by Mark Potashny and by Wally Gilbert at Harvard. And so we had the very first promoters. And so we wanted to know, were they the same? Did eukaryotes use exactly the same sequences to start making RNA? And Richard Gelinas came to my lab, started working with adenovirus 2 messenger RNA. We spent a lot of time looking to see if this could be done using a method that I came up with that would isolate and characterize the extreme end of the RNA so that we could then map that back onto the viral DNA and see what sequences were upstream on it. Well, we tried very hard to do that. It didn't work with early RNAs, but it turned out that it did eventually work with late messenger RNAs. And what we discovered was that in late adenovirus messenger RNAs, of which there were at least 10 or 12, that they all had exactly the same 5' end on them. Every one of them was the same. And this was a quite extraordinary finding, and we didn't know why. We were not sure whether this was because this sequence was just repeated in the DNA, or whether it was because there was a priming RNA that contained this sequence and that it just started making the rest of the RNAs. We spent a lot of time trying to figure out what was going on. And it wasn't until 1977, that we really came up with the experiment that would prove what was going on, and it was something called an R-loop experiment. If you look at the top right, when you hybridize an RNA to the DNA that codes for it, it forms what is known as an R-loop. And this R-loop is stable for the simple reason that DNA-RNA hybrids are more stable than DNA-DNA hybrids. Now, because we were looking at a messenger RNA, we knew that at the 3' end of the messenger RNA, there was this poly A sequence. And so it wasn't coded in the DNA, it was added after transcription, and so it wouldn't hybridize, and so it would stick out as a tail from this R loop. And we thought that if there was a primer at the 5' end, then the primer would still be binding to the R loop, and it would stick out at the 5' end. So we did this experiment. I should say we did it. We made the reagents to do it. And then fortunately, because neither Richard nor I were electron microscopists, we had two electron microscopists, Louise Chow and Tom Broker, who worked in a lab close to ours. And I thought of this experiment on a Saturday morning. We went down and talked to them. And they said, well, the experiment you propose has never really been done before, but let's do it. We think it should be doable. And so they said, if you make these reagents, then we will do it. So on the Tuesday morning, we had the reagents made. I should say Richard had the reagents made. He did the experimental work. And then we had a probe DNA, a DNA that we thought might code for the primer. And so if it did, it would also form a structure shown in the middle where the green probe DNA would hybridize to the extension from the 5' end of the messenger RNA. Well, we made the probe DNA, we made the R loops. Louise Chow did the experiment. She took the electron micrograph picture, but the picture at the bottom shows what she found. Instead of this probe hybridizing at just one place, it hybridized at 2 places, and there was a loop in between. And this was the discovery of something that we call RNA splicing. We already knew from a year's worth of biochemistry that all of the RNAs in adenovirus were like this. We just didn't know the structure. We knew that they had something at the 5' end that was not coded next to the messenger RNA. And this really showed us that what was going on was that it was a much more complicated process to make RNA in eukaryotes than we had ever realized. What was going on was that the genes, instead of being a nice contiguous sequence as they were in bacteria, were actually split into pieces. And this became known as split genes. This discovery of RNA splicing was made in 1977. We made it in the beginning of March. It was published in September. And the experiment, the paper was called An Amazing Sequence Arrangement at the 5' ends of adenovirus 2 messenger RNA, because it had this very unusual split structure. Now, I should say when we sent this paper in for review, we got a lot of criticisms back from reviewers. Actually, even my fellow authors didn't really like use of the word amazing. They said that, this is not something we use as scientists. This is not a scientific word. And so the reviewers said, you should change it, use a different word. And the editor, Ben Lewin, said the same thing. Well, after we got the reviews back, I called up Ben Lewin, the editor, and I talked to him about one or two other points that the reviewers had raised. And then during the conversation, I said, when you first saw this, what did you think? He said, oh, it was amazing. I said, I rest my case. And at this point, he agreed that we could use the word amazing in the title of this paper. And to the best of my knowledge, this is the first time this was ever used in the title of a scientific paper. So I'm rather pleased about that. So that was very good. Late in 1977, people were already talking about Nobel Prizes because it turned out this discovery was made elsewhere, and pretty soon it became apparent that all eukaryotic RNAs had this business of RNA splicing. They were just not contiguous genes. The genes were split into pieces. Well, to cut a long story short, this led to the award of the Nobel Prize. Next slide, please. And this was given in 1993 and shared between myself and Phil Sharp, who had independently made the same discovery when he was a professor at MIT. So this was all very nice. I have to say, I recommend this to everybody. You go to Stockholm. We spent 10 days there. Pretty much every day there was a very special party that took place. The sort of thing, whether it was lunch or dinner, it was the thing, it would have been the highlight of the year if it was the only thing that happened during the year. And to have this go on for so long was really quite disturbing. Anyway, it was fun. So when you go, you have to give a talk. And I'd not actually worked on RNA splicing for many years. And instead, we'd started working with DNA methyltransferases. And just before I had to go and give my Nobel talk, we made another interesting discovery with the crystallographer Xiaodong Cheng, and showed that when proteins that are going to methylate DNA, when they bind to the DNA, they flip the base right out of the helix and into an active site in the enzyme. And this was the discovery, the first time that base flipping had ever been seen. And we now know that it's quite common when things, when proteins interact with DNA and want to do some chemistry on the bases. Now, I want to go back and talk about restriction enzymes because these turned out to be the foundation of the biotech industry and were very important. I tried to persuade Cold Spring Harbor in order to make a company and start selling these things with the profits going back to Cold Spring Harbor. Jim Watson said he wasn't interested, he didn't want to do it. I ran into Don Combe, and in the process, he had already started a small company in this basement underneath a hairdressing salon in Beverly. And he and his wife and one technician had started making reagents for research. He'd made one restriction enzyme, and I told him at the time we had 30 that we discovered, and I said I thought there was a good business here. Went up, talked to him, and he agreed and hired me as the chief consultant at the time. This was back in 1975. Next slide, please. This was the first catalog ever to sell restriction endonucleases. The company now is quite old, it's 49 years old, been continuously profitable. Sal Rossello, shown on the right, is the CEO, and most of the staff are scientifically trained. We're a very cooperative environment. We're very much a family company, if you like. One thing that we did and are rather proud of is that when the vaccines were needed for COVID, we ended up making 4 of the reagents that were absolutely critical to Moderna and Pfizer for producing the vaccines. 3 methyltransferases to methylate the cap that goes on to messenger RNA, and then the RNA polymerase that is used to make the RNA. After the prize, I've done many things. I learned that people listen to me when I talk, as you are doing now. But whereas they used to listen to me, they also sometimes act on what I say. I love games. I put a croquet lawn in front of my house. That's what I use my Nobel Prize money for. And I've also done a lot of fun things, including participate in the Ig Nobel Prizes at Harvard University. These are prizes given for science that first makes you laugh, but then you realize it's serious. I've had a number of honors. I was knighted by Prince Charles, now King Charles, and I have done a number of good causes with the Nobel laureates, including helping to gain the release of Bulgarian nurses from death row in Libya, and also a number of other movements that have been successful. Let me just go over the importance of luck and failure. Billiards I talked about, Kazum Kurosawa I talked about. I went to Harvard, not Wisconsin. Looking for eukaryotic promoters in adenovirus. When we first started, the experiments failed, and we had to find a new way of doing it. And we discovered this because we looked closely to see why we failed. And that is really very important. I also probably have the luckiest break of all. I took an early plane. You may remember in 9/11, the plane of these hijackers went into the World Trade Tower. I was booked on that plane until 2 weeks before it took off. I was going to a meeting in California when the meeting got moved forward by 1 day. And so I took that plane. I was in California and saw the crash at the time on television. And finally, studying bacterial RM systems really has led to just tremendous luck throughout my life. I'm now the Chief Scientific Officer at New England Biolabs, and they've been great. We have 170 Nobel laureates supporting GMOs. These are things that are just incredibly important. It's my latest big mission. I go around talking about the importance of GMOs if we're ever going to feed the world. And I want to finish by talking about 3 books and a movie. And these books are books that I think everyone should read. And they're important. And the picture of Scientist is a documentary. It's available on, I think, Netflix, but it's certainly available fairly easy to find. But the 3 books talk about the bias that has been that women have been exposed to as scientists. The Exceptions is a book about Nancy Hopkins, who is a good friend of mine, and she discovered that women were being discriminated against at MIT. She organized the women. They went and talked to the head of MIT at the time, and he changed the rules. And it's really a very inspiring story. But at the same time, it's heartbreaking when you see the way that she was treated as a young faculty member. Kathleen Carrico, Cathy Carrico, recently published this autobiography talking about her life in science. And she won the Nobel Prize last year for the discovery of messenger RNA. And her story is really very extraordinary. And even now, she's not been properly rewarded, even though she's a Nobel Prize winner by the scientific community. The 3rd book on the right came out a few years ago about invisible women, and by this lady who has documented with good data the bias that exists in the scientific world in a world designed for men. And it's not just about science, it's about many other aspects of life. And the reason I recommend these is because I know in my own life that I have discriminated against women from time to time, not deliberately, because I thought I was doing a good thing. But I'll give you one example. We think that if we treat women as though they were men, that we're actually treating them equally. But they're not men. They have all sorts of other problems. I shouldn't say problems, they have features of their biology. They get married, they have children, they have periods. They are not men. And we need, when we think and treat women in the scientific world, we need to remember that they are not men. And we have to make sure that we adjust for the different lifestyles that they have and don't treat them badly. I think it's high time that we realize that in many ways, women are better than men at a lot of things that they do and that we do. And so I'll stop at that point. I thank you for your attention. I'm sorry about the break that took place, but I'll be happy to answer any questions that may come your way. Thank you.
Thank you so much, Professor Roberts. So, given the slight time crunch that we're now under, I want to quickly ask one question from me, and then I'll get one or two questions from the audience. One is, I just want to, given sort of the final things that you have said, Professor Roberts, do you have any sort of words especially perhaps for young women researchers sort of coming into science, words of advice of how to sort of navigate this this environment that continues to be somewhat challenging and biased, and any sort of words of encouragement or advice for young researchers in that respect.
Well, I think reading those books, you will get some idea of what can go on, and also give you some idea of how to deal with it. I think particularly the exceptions by Nancy Hopkins, or by Kate Zanicki about Nancy Hopkins, is really very important. And looking at the movie, the documentary, Portrait of a Scientist, is very, very interesting. You will find ways in which you can deal with it. But I think the key thing is not to go into a career as a woman thinking that you are not as good as men. And I think very often what happens in families, also at school, is women are often treated as though they're somehow lesser than men. And you're not. You're absolutely not. And so this business of self-confidence and knowing that you are absolutely equal to the men that you're dealing with is really, really very important. So don't let men put you down. Tell them if they're misbehaving.
Excellent. So let's get one or two questions from the audience. So if you would like, you can sort of come here and ask the question to Robert yourself, and feel free to introduce yourself very briefly.
Yeah. Hi, I'm Lucy, and I had a question that after your Nobel Prize, did you continue research into the role of introns and gene expression and then that side of genetics as well?
Okay, well, after we made the discovery in '77, we tried to set up an in vitro system to study splicing, but we were beaten to the punch by a good friend of mine called Tom Maniatis, and he picked a better system to study it than I did. And so we slowly stopped working on splicing because others were going ahead. And I got very interested in DNA methylation. DNA methylases are companions of restriction enzymes. And so I've really since then focused my research on DNA methylation, and I still do that today. That's exactly what I do every day today, is to study DNA methylation.
Thank you very much.
You're welcome.
And we have one more question here coming up. Feel free to introduce yourself as well.
Hi, I'm Tanya Brass. You said that recombinant DNA, using it to make GMOs, is basically. Is there no way that it can be like manipulated?
I can't hear you very well. Can you speak up a little bit, please?
You said that recombinant DNA and using it to make GMOs is basically safe. Is there any way that it can be manipulated and can become harmful to people? Is there like?
Well, absolutely. I mean, do you know anything that can't be manipulated by bad people to cause trouble? I think artificial intelligence, which is a very hot topic at the moment, is something it can be used for good or for bad. Just like nuclear power can be used for good, it can be used for bad. So you could certainly imagine using GMOs in order to maybe manufacture dangerous viruses, manufacture plants that are poisonous. A lot of plants are naturally poisonous. So you could take the genes that encode the poisons and put them into a plant. But I think we have to assume that for the most part, people are trying to be good. They're trying to do good things. And the nice thing is that you can always test whether people are making something that is bad. I always say with viruses, you could engineer a smallpox virus very easily. And all you would need to do to find out who was doing it was look for a lot of dead terrorists, because they probably would kill themselves first, I'm glad to say. But in general, the GMOs that we use to make plants are really designed to be very safe. There's not been a single incident in 30 years where there's been a problem. And millions of people literally have eaten GMO plants. In the US, they're very, very common. Corn is very common. In Europe, even though people have been told that GMOs are dangerous, they're really not. It's just a campaign by Greenpeace because it's helped them to make a lot of money by being opposed to GMOs. And Europe doesn't need GMOs. Europe's got good food, although that is changing. You may or may not know that the grapes that champagne is made from don't grow very well in Champagne anymore. They're starting to grow them in the south of England because of climate change. But we could fix that. It would be possible to make grapes that would be useful for champagne, that would be heat resistant, and would be able to grow back in Champagne again. But the real problem for me is not so much that, it's that in the developing world, if they don't adopt GMOs and increase the yields and the nutritional value of plants, there's going to be a lot of hunger, there's going to be a lot of malnutrition. And for Greenpeace to be opposed to that is terrible. They literally are killing millions of people every year by refusing to let some of these countries grow GMO plants. And finally, I find that morally repugnant. I'm sorry, it's terrible. I don't know how they sleep at night.
So I think we have time for maybe one more question. If well, students in priority, but if not, you're very welcome to ask your question as well. Please, yeah.
Hi, sir. Robert, can you hear me?
Yes.
Hey, very, very insightful talk. And I think you've been very humble to ascribe a lot of your success to luck. But if I may ask on younger people's behalf, what are some of the traits you would like them to develop and focus on to get success despite luck or even bend the luck in their favor? Because luck is something you can't control, but what can they do? What are the traits you would like them to focus on despite the luck or other than luck?
Okay. Well, so I mean, I think curiosity is a good thing. And don't be disappointed when you fail. If you fail, then make sure you learn from that failure. So go back, figure out why you failed, and make sure you don't repeat that same mistake again. But do look back and think, when something lucky happens, can I take advantage of this? How can I take advantage of this? So many people have a lucky break. You know, they're playing tennis, ball hits the net, just drops over. And then when it comes for them to serve again, they somehow feel guilty that they had the luck and that the other person didn't. And don't. Everybody has luck. Everybody. And the fools are the ones who don't take advantage of it. So take advantage of it when it comes your way.
Thanks a lot.
Okay.
Thanks again.
Okay, so Professor Roberts, I wonder if you have just any parting words for the student researchers in the room. Our organization is really sort of focused on sort of helping young people discover science and academic research for the first time in their lives. I wonder if there's any sort of closing words of wisdom that you would like to leave with the students.
Okay, well, you know, I always tell students you need to find out what you really love to do. What is it that you're absolutely passionate about, and then make a job of it. And I don't care what it is that you're passionate about, you can always find a way to make that your career, to make it a job. Maybe you like playing games. Figure out how to write computer games so that you make your own games. Whatever it is, you can always find a way to fulfill it and to make it acceptable. There are many, many things that you can do. And don't think that what you're doing at the moment or what your parents said you should do is necessarily the thing that's good for you. You know what is good for you. Your parents often don't know what is good for you. So follow your own feelings and follow your own passions.
Thank you so much, Professor Roberts.
Okay.
Let's give one more round of applause. And we here at CCIR would again want to thank you for your time. There is another speech going on in the other room in 2 minutes, so feel free to rush over. But Professor Roberts, thank you so much.